The theory of classical singularities in general relativity is a continuing philosophical and scientific problem, asking whether singularities truly exist in space-time, whether the Big Bang was one, and whether such cases expose limits in general relativity. Newtonian gravity, special relativity, and general relativity are connected through a geometric view of motion, where inertial movement can be described through geodesics or world lines in space-time. Because inertial and gravitational mass are equivalent, gravity can be treated geometrically rather than simply as a force. This leads to Newton-Cartan theory, which reformulates Newtonian gravity in curved space-time using covariant ideas. Newtonian geometric gravity is then treated as a limiting case of relativistic mechanics, while special relativity replaces Galilean invariance with Lorentz invariance when gravity is negligible. Light cones give space-time its causal structure, marking which events can influence one another without faster-than-light signals. Together with the world lines of freely falling bodies, these light cones help reconstruct the space-time metric up to a scale factor. When gravity is included, the straight temporal lines of an inertial frame become curved, showing that gravity changes space-time geometry itself. Proper time in a gravitational field, therefore, cannot be described by the flat Minkowski metric of special relativity. A more general pseudo-Riemannian geometry is needed, along with the Levi-Civita connection, while local regions still behave approximately like Minkowski spacetime. Einstein's 1915 field equations are then introduced as the mathematical framework, explaining how matter and radiation influence the geometry of space and time. In general relativity, gravity is not an ordinary force, but a manifestation of local space-time geometry. Einstein's equations relate the geometry of a four-dimensional pseudo-Riemannian spacetime to the energy-momentum content within it. Matter and radiation curve spacetime, and the curved spacetime determines how objects move. For weak gravitational fields and slow speeds, general relativity reduces to Newton's law of universal gravitation. General relativity is generally covariant, meaning its laws keep the same form in all coordinate systems. General relativity lacks fixed background geometric structures, since space-time geometry itself is dynamic. Solutions of Einstein's equations are therefore models of possible universes, sometimes with additional assumptions about matter. There are exact solutions such as Schwarzschild, Reissner-Nordström, and Kerr black hole spacetimes, as well as cosmological models like Friedmann, Lemaitre, Robertson-Walker, de Sitter, Gödel, Taub-Enut, and anti-de Sitter spacetime. In contrast, in Newtonian, gravity mass is the source of gravity, with relativity, where energy density, momentum density, pressure, shear, and curvature tensors all enter the gravitational description. While alternative theories such as Brans-Dicke theory, teleparallelism, FR gravity, and Einstein-Cartan theory modify or constrain the same basic ideas.